Right now, as you're hearing this, the universe is exposing a gap in what you were taught about gravity. You grew up with a simple rule: gravity pulls on mass, heavy things fall, planets orbit. At the same time, you were also told that light has no mass. It's pure energy. Yet, we have direct observations where light clearly does not travel in straight lines near massive objects. It bends around the sun, it curves around galaxies and clusters, it forms arcs and rings on deep space images. So if gravity is supposed to care only about mass, and light has none, there's a clear conflict. Either light is secretly massive, or our basic idea of gravity is incomplete. Let's start with the core claim you've heard: light has no mass. In proper physics language, that statement really means light has no rest mass. It can never sit in a frame of reference where a photon is at rest. It always moves at the speed of light. However, even without rest mass, light carries energy and momentum. You see that in real effects. Radiation pressure can push on objects. Solar cells accelerate when sunlight hits them. Lasers can exert tiny forces on mirrors. So it's wrong to think of light as physically weightless in every sense, in the old Newton-style gravity picture. Though gravity is a force between masses, the strength is proportional to the product of the masses and falls off with distance. In that framework, if something's mass is strictly zero, the force on it should be zero. That's the root of the paradox. The math of the old theory says gravity should not do anything to truly massless light, but the universe does not agree. The cleanest early test of this tension came in 1919, during a total solar eclipse. Arthur Eddington and his team used the eclipse as a chance to measure whether the sun deflects starlight. They had photographs of a region of sky taken months earlier, when the sun was nowhere near that patch. They measured the positions of several stars in that field. Then, during the eclipse, when the moon blocked the sun's glare, they imaged the same region again, this time with the sun in front. If gravity bends light, the apparent positions of those stars should shift slightly, because the light from them, passing close to the sun, is deflected before reaching Earth. The result, after careful analysis, was that the stars appeared displaced outward by an amount of roughly 1.75 arcseconds for light grazing the sun's limb, tiny on the sky but measurable, and importantly that value matched Einstein's prediction from general relativity and was about twice what a patched-up Newtonian model would give, where you fake a mass for light based on its energy. In other words, if you stubbornly try to keep Newton's idea and you say, fine, let's pretend light has an effective mass equal to its energy divided by c squared, and then plug that into Newton's force law, you do get some bending, but only half as much as what was observed. That is not a small detail. It's a sign that the whole framework is the wrong tool for this job. Einstein's theory, by contrast, never treats gravity as a force acting through space. Instead, it says mass and energy, curve, space, time, and free-moving objects, including photons, follow the straightest possible paths called geodesics. In that curved space-time, when you compute what that implies for light passing near the sun, you naturally get the full 1.75 arcseconds. No hacks, no fake mass for photons. The success of the eclipse measurements was one of the first big public confirmations that the gravity only pulls on mass picture had to be replaced. Over the last few decades, this has been confirmed again and again, with far more precise and dramatic examples. Hubble and JWST images of the distant universe show massive galaxies and galaxy clusters acting as gravitational lenses. Light from background galaxies travels through the curved space-time created by the foreground mass and arrives at Earth from different directions. As a result, the background objects appear stretched into long arcs, sometimes duplicated into multiple images and in special alignments, almost perfect rings called Einstein rings. None of this requires light to gain mass, or to experience a separate gravity on photons force. What is happening is that space-time near the massive cluster is not flat. The path that light can take a bent. When you solve Einstein's equations for that situation, the predicted deflection angles match the shapes and positions of the observed arcs and rings. so well that astronomers can invert the problem and use the lensing patterns to reconstruct how mass, including invisible dark matter, is distributed in the cluster. This is the important point. The amount of bending depends on the total mass and energy present, not on what it's made of, whether it's stars, gas, or dark matter. Light behaves as a probe of spacetime geometry. It doesn't selectively care about the type of matter, it responds only to the curvature. This is fundamentally different from thinking of gravity as a mysterious pull acting only on massful particles. In the modern view, the sunbending starlight and a cluster warping galaxy images are the same effect, operating on different scales. Evidence that space-time is curved by energy and momentum, and that photons, despite having no rest mass, must still follow the geometry. So when you put all this together, the starlight deflection in 1919, the many gravitational lensing systems we map today, the consistent agreement between observation and the predictions of general relativity, the slogan "gravity only pulls on mass" clearly fails. The correct summary is gravity, in Einstein's sense, is not a force on a mass. It is the curvature of space-time produced by energy and momentum. Light has no rest mass, but does have energy and momentum, and whatever follows from the curvature it must obey. That's why light is affected by gravity. Without ever giving photons a mass sticker, the lie you are told is not that gravity exists, but that it only cares about mass, and that simplification breaks the moment you test it against how light actually behaves near massive objects. When you read or hear that light has no mass, the precise statement, in physics language, is that light has no rest mass, meaning there is no frame of reference in which you can travel alongside a photon and see it sitting still. For a massive object like an electron or a rock, you can in principle move with it, and in that special frame its kinetic energy is zero. The remaining energy is tied to its rest mass. For light, that rest frame does not exist. Photons always move at the speed of light in vacuum, so their rest mass is defined to be zero. However, this does not mean light is physically empty or passive. It still carries energy and momentum, and those are real measurable quantities that can push, not, and transfer motion to other systems. Einstein's famous relation E equals mc squared is often taught in a one-way direction. Mass can be seen as a form of energy, but in special relativity the more general statements are that total energy and momentum form a 4-vector, and that for a particle with rest mass m, you have E squared equals pc squared plus mc squared squared. For a photon, m equals 0, so the relation reduces to E equals pc, where p is the magnitude of its momentum. This tells you immediately that a photon with energy E has momentum p equals E over c. There is no mass in that expression, yet the momentum is not zero. This is why light can exert pressure. This is why it can change the motion of matter. Experiments directly confirm this. Solar sails deployed in space experience a tiny but continuous push from sunlight. Laser beams in optical cavities press on mirrors and can be measured by sensitive instruments. In the photoelectric effect, light hitting a metal surface transfers energy to electrons, ejecting them from the material. The key point is that no rest mass does not mean no dynamical impact. In laboratory physics, the fact that photons carry momentum shows up clearly in laser cooling and trapping. These setups, atoms move in a vacuum chamber, and multiple laser beams are tuned slightly below an atomic transition. When an atom moves toward one of the beams, it sees the light Doppler shifted closer to resonance, absorbs a photon, and then re-emits one in a random direction. Each absorption event transfers one photon's momentum to the atom, slightly reducing the component of its velocity along the beam direction. Because the re-emission is random, those kicks partly cancel over many cycles, but the directed absorption always pushes against the atom's motion. With enough photons repeated millions of times per second, the random motion of the atoms is reduced to micro-Kelvin temperatures, far colder than typical lab environments. This entire technique only works because each photon, despite having zero rest mass, delivers a small but precise momentum change, scattering event by a scattering event. You see similar momentum transfer effects on much larger astrophysical scales, where we talk about radiation pressure. Whenever light is intense and confined, it exerts a pressure on matter. In the accretion disks around black holes, neutron stars and massive young stars gas spirals inward under gravity. As it falls, gravitational energy is converted into heat and radiation. The intense outgoing radiation pushes outward on the surrounding material. If the luminosity becomes high enough, this radiation pressure can balance gravity or even overcome it, driving powerful outflows. For very luminous objects, there is a theoretical limit called the Eddington limit, beyond which steady accretion becomes difficult because radiation pressure pushes gas away. Observations of quasars and luminous blue variable stars show strong winds and outflows, not primarily caused by explosions, but by the continuous push of high-energy photons transferring momentum to gas and dust over time. Putting these examples together, you get a clear picture. Light without rest mass still behaves like a carrier of energy and momentum. It can change velocities, cool gases, push on sails, regulate the growth of black holes and stars. All of this matters when we talk about gravity, because in Einstein's framework, the source of gravitational effects is not a single scalar quantity called mass. Instead, the source is the energy-momentum tensor, a mathematical object that includes energy density, momentum density, pressure, and stresses in all directions. Einstein's field equations roughly say that spacetime curvature is proportional to this entire tensor, not just to rest mass. So if something has energy and momentum, it contributes. Light satisfies that condition, even with μ equals 0, as energy density, momentum flow, and pressure. So in the modern view, it is entirely natural that light is seen by gravity. Einstein's move was to stop treating mass as a special isolated quantity, and to generalize the idea of gravitational charge to all forms of energy and momentum. Your old mental habit of thinking gravity cares only about mass is really a leftover from Newtonian gravity, where mass appears in the force law as the only source term once you upgrade to general. Relativity. The correct statement becomes gravity responds to the full energy momentum content of spacetime, light with zero rest mass. But non-zero energy and momentum fits smoothly into that picture. It does not need a hidden mass. It does not require an exception. It simply follows the paths determined by the curvature created by all energy and matter around it. That is what it actually means, for light to have no mass, in a universe where gravity is geometry, and the source of that geometry is energy in all its forms. In Newton's framework, gravity is described as a force that acts between objects with mass. The strength of the gravitational force between two bodies is given by F equals gm1 m2 over r squared, where m1 and m2 are the masses, r is the distance, and g is the gravitational constant. This law works very well for planets, moons, falling apples, and most everyday situations. However, it has an immediate conceptual problem with light. If a photon has zero mass, then when you plug m equals 0 into Newton's formula, the force on it should be 0, meaning gravity should not affect light at all. That is already at odds with the observations of light bending around massive bodies. People tried to repair this by saying light has energy and energy is equivalent to mass, and then assigning an effective mass equals E over c squared to the photon. But this is an ad hoc fix. It is not derived from a deeper Newtonian principle about fields or spacetime. It is just an attempt to shoehorn new facts into an old formula. Beyond this, Newton's theory assumes that gravitational influence acts instantaneously at a distance. If the sun were to move suddenly, Newtonian gravity says the Earth's gravitational pull would update immediately with no time delay. in a universe where information cannot travel faster than light. This becomes a serious inconsistency, special relativity, which came before general relativity, already tells us that no signal can propagate faster than the speed of light, so a modern gravity theory must respect that. Newton's form does not. It treats space as an unchanging background and gravity as a force sitting on top of that background. There is no concept of space-time itself being dynamical or curved. This is another reason why the Newtonian picture hits a wall when we bring in light and high-precision measurements. When you apply the effective mass hack to light and treat a photon as a very fast, very light particle moving through the sun's gravitational field, you can compute how much its path should bend in Newtonian gravity for a particle with speed close to c, passing at some minimum distance from the sun. The predicted deflection angle comes out to a certain value. When Einstein did the same calculation, within general relativity, he found that the predicted bending for a light ray grazing the sun should be about 1.75 arcseconds, which is twice the Newtonian value, roughly 0.87 arcseconds. The key experiment, the 1919 solar eclipse observations led by Eddington, measured the apparent positions of stars near the sun during the eclipse and compared them with their positions when the sun was elsewhere. The shifts they found were consistent with Einstein's full value, and not with the half-sized Newtonian prediction. This half-bending problem is a clear, quantitative failure of Newtonian gravity in the regime where light is involved. It is important to emphasize that this is not a small correction within Newton's theory. It is not the case that you can tweak a constant or add a tiny term and make the numbers fit. The factor of two difference emerges because in general relativity, both the curvature of space and the curvature of time contribute to the deflection of light, while a Newton-style approach only captures part of the effect. In Einstein's picture, space-time is a four-dimensional entity, and the geometry itself dictates the path that objects and light follow. In a Newtonian view, gravity is a force in flat space acting on particles, and light is not naturally part of that scheme. This mismatch in conceptual structure shows up as a concrete mismatch in the predicted bending angle, and observations choose the relativistic value. The trouble for Newtonian gravity does not end with light. Mercury's orbit provided another independent clue that something deeper was missing. As Mercury orbits the Sun, its closest point to the Sun, called the perihelion, slowly shifts over time. This is known as perihelion precession. Most of this precession can be explained by gravitational tugs from other planets. Within Newtonian gravity, when you account for all known influences, there is still a small residual precession left over, about 43 arcseconds per century. This discrepancy was a long-standing puzzle. In the late 19th century, some proposed additional unseen planets or modified distributions of mass, but none of those ideas held up cleanly. When Einstein applied general relativity to Mercury's orbit, he found that the curvature of space-time near the Sun adds exactly the missing 43 arcseconds per century, closing the gap between theory and observation without adding arbitrary new objects. So by the early 20th century, physicists had two very different stubborn facts that Newton's gravity could not properly handle: light bending near the Sun and Mercury's anomalous perihelion precession. Both effects were small but measurable, and both pointed in the same direction. The old notion of gravity as an instantaneous force between masses in flat space was no longer sufficient, the data were telling us. The gravity interacts with light in a way the old equations cannot support, and that the motion of planets in strong gravitational fields deviates slightly, but systematically. From the Newtonian predictions, these were not just numerical glitches, they were signs that the underlying picture of what gravity is had to be revised. Einstein's response was not to patch Newton's law, but to replace the whole framework. Instead of treating gravity as a force, acting within a fixed stage called space and time, he proposed that mass and energy change the structure of space-time itself. In general relativity, The presence of energy momentum tells spacetime how to curve, and this curvature tells matter and light how to move. Free-falling objects follow geodesics, which are the straightest possible paths in this curved spacetime. For massive objects, these are called time-like geodesics. For light, they are null geodesics. Once you adopt this view, the old question, how does gravity pull on light if light has no mass, is no longer the right question. There is no separate pulling force working on a photon. Instead, light always moves at speed c locally, along paths defined by the geometry. If space-time near a mass is curved, those paths are not straight lines in the Euclidean sense, and to an observer far away they appear bent. The sun does not grab the photon simply travels through a region where space and time are not flat. Newton's gravity breaks here, because it never let gravity modify space-time itself. Einstein's theory succeeds precisely because it does. When we say that light follows the straightest possible path in curved spacetime, it helps to first fix what we mean by straight. On a curved surface on Earth, the shortest route between two distant cities is not a straight line on a flat map, but a great circle, like the path that follows a line of longitude cutting the globe. An airplane flying that route is not constantly turning because a force pushes it sideways. It is just following the natural shortest path, allowed by the curved geometry of Earth's surface. If you then project that path onto a flat map, it looks curved only because the map is flattening something that is not flat in general. Relativity, space-time plays the role of that curved surface, the natural paths through it are geodesics, and light follows null geodesics. Locally, these are as straight as possible, but when you draw them on your mental flat picture of space and time, they can look bent near massive objects. The curvature is stronger, so the geodesics curve more, and we see that as light bending around stars and galaxies. Einstein's equivalence principle gives a very clear way to connect gravity with acceleration. It states that locally, being in a uniform gravitational field is indistinguishable from being in an accelerating frame. Consider a rocket far from any stars or planets, accelerating upward with constant acceleration. If a beam of light enters one side of the rocket horizontally and travels toward the opposite wall, you standing inside will see the floor move upward while the light is in flight. By the time the beam reaches the other side, the floor has risen, so the beam hits slightly lower than where it entered. To you inside, it looks as if the light followed a curved path bending downward, even though in the outside non-accelerating frame the light moved in a straight line. This is a simple consequence of mixing uniform motion and acceleration. Now replace the accelerating rocket with a stationary lab sitting in a gravitational field like on Earth's surface, the equivalence principle says. Locally, the physics is the same, so a light beam crossing a room near a massive body will also appear to curve downward, not because a force is yanking on the photon, but because the geometry of space-time in that region is equivalent to the accelerating frame picture. These ideas are not left as abstract stories, they are direct, precise experiments that test the way light behaves. In a gravitational field, one classic example is the Pound-Rebka experiment, performed in 1959 at Harvard. They used gamma-ray photons emitted by iron nuclei at the bottom of a tower and detected them at the top over a height of about 22 meters, according to general relativity. As light climbs in a gravitational field, it loses energy, not by slowing down, but by its frequency decreasing. This is called gravitational redshift. Pound and Rebka used the Mossbauer effect, which allows extremely precise measurements of gamma-ray frequencies. They found that the photons arriving at the top were slightly redshifted by exactly the amount predicted by general relativity. To make them resonant again with the absorber at the top, they had to move the source to add a Doppler shift that cancelled the gravitational shift. This was a laboratory scale confirmation that gravity affects light's frequency and energy in line with the curvature picture. Later experiments extended this to clocks. which are ultimately physical systems that count cycles of some regular process, atomic clocks, on airplanes and satellites, tick at rates that depend on their position in Earth's gravitational field. A clock higher up, where the gravitational potential is less deep, runs slightly faster than an identical clock on the ground. When you send light signals between them, their frequencies and arrival times show exactly the shifts. General relativity predicts. This is again consistent with the idea that time itself is part of the space-time geometry and flows at different rates, at different altitudes. Light moving through that geometry has its frequency and phase adjusted accordingly. There is no need to invoke any special force on photons. The behaviour follows from the structure of space-time and the requirement that light travels along null geodesics. A practical everyday system that depends critically on these relativistic effects is GPS, the Global Positioning System. It uses a constellation of satellites orbiting Earth. Each satellite carries very stable atomic clocks and continuously broadcast timing signals. These signals are radio waves, a form of light travelling at speed c. Your receiver on the ground listens to several satellites at once and computes its position. From the travel times of those signals, if we treated gravity as purely Newtonian and ignored general relativity, we would assume that all clocks, on satellites and on the ground, tick at the same rate. In reality, satellites are higher in the gravitational field, so gravitational time dilation makes their clocks run faster. At the same time, they are moving relative to the ground, so special relativity makes their clocks run slower. The net effect is a small but significant difference. On the order of tens of microseconds per day, engineers must pre-adjust the satellite clocks and continuously correct for these relativistic shifts. If they did not, the errors in timing would accumulate, and the computed positions would drift by kilometers per day. The system only works because we accept that space-time is curved, that time flows differently with height, and that light signals follow that geometry exactly as general relativity says. All of these examples, the thought experiment of the accelerating rocket, the lab-scale gravitational redshift measurements, the behaviour of atomic clocks in different gravitational potentials, and the functioning of GPS point in the same direction. Gravity is not best described as a force pulling directly on objects with mass. It is better described as the curvature of space-time, which dictates how free-moving systems, including light, evolve. When you think in those terms, riding a beam of light through curved space-time means acknowledging that the beam always moves at speeds locally, but its path and frequency are shaped by the geometry near massive bodies. The path is not a straight line in the old Euclidean sense, and the timing of signals is not uniform across heights. These are concrete, measured facts. They are built into technologies you use every day, and they provide strong, consistent support for the view that light is affected by gravity, because it travels through curved space-time, not because it secretly has mass or feels a special force. In general relativity, the basic rule for motion is simple and strict. Everything moves along the straightest possible path available to it. In space-time, these paths are called geodesics for objects with mass that experience the passage of time along their world lines. The paths are called time-like geodesics for light, which always moves at speed c and has no rest frame. The paths are called null or light-like geodesics. The important detail for you is that the definition of straightest here is not something you choose object by object. It is dictated entirely by the geometry of space-time, encoded in the metric. Once the metric is fixed by the distribution of energy and momentum, the geodesics are fixed. Planets, photons, and even gravitational waves then simply follow those paths. There is no extra instruction that says apply a different rule to light. Light does not need mass to be guided by the geometry. It just obeys the same geodesic law applied to a null trajectory. When you think in Newtonian terms, an object in a gravitational field can respond to the force By changing its speed and direction, for example, a falling rock speeds up as it drops, and its trajectory curves toward the Earth, a satellite in orbit. Has its direction constantly changed by gravity, even if its speed stays roughly constant? For light, the situation is constrained. Locally, in vacuum, light must always move at speed c. It cannot be accelerated from below to reach c, and it cannot be slowed down from c to a smaller value, while still being a free photon in empty space. That speed is built into the structure of space-time itself, so gravity cannot act on light. By changing its speed, the only way for gravity to influence light is through the shape of the path. If space-time is curved near a mass, the null geodesics themselves are bent. Light follows them, so its direction changes. When you see a beam of starlight deflected near the Sun or arcs of galaxies around a cluster, what you are really seeing is not a force tugging directly on photons, but the geometry dictating a curved null path. Another key observable effect that shows how light feels gravity is gravitational time delay, also known as Shapiro delay. When a light signal, such as a radio wave, passes near a massive object like the Sun or a planet, its path through spacetime is effectively longer than it would be in flat spacetime. There are two pieces to this. The spatial path can be bent, increasing the geometric distance, and the time component of the metric is modified so that clocks along the route tick at different rates. Together, these effects mean that the travel time for the signal is slightly increased compared to what you would calculate, assuming straight-line propagation at speed c. In a flat background, Erwin Shapiro proposed this test in the 1960s, and experiments were done by bouncing radar signals off planets like Venus or Mercury. When the signals pass near the Sun on their way, the round-trip time is a bit longer, by tens or hundreds of microseconds, than the flat spacetime prediction. Measurements of this extra delay match the quantitative predictions of general relativity. Very well, again this is achieved without giving the photon a tiny mass. It follows from the altered spacetime geometry alone. The same principle is used when we track spacecraft signals as they pass behind the Sun or other massive bodies. The radio signals experience both bending and time delay. By fitting the received timing data with models based on general relativity, mission teams can correct for these effects and navigate accurately. If gravity were just a Newtonian force on masses, with spacetime left flat, there would be no natural reason for such a path-dependent time delay for massless signals. The fact that the delay appears, with the size and dependence predicted by curved spacetime, is strong independent evidence that light is responding to geometry, not to some added-on force term. There is also a deeper aspect to how light and gravity relate, which comes from Einstein's field equations themselves. Schematically, they can be written as g mu nu equals open parenthesis 8p g divided by c to the fourth power close parenthesis t mu nu, where g mu nu describes the curvature of spacetime, and t mu nu is the energy-momentum tensor. This equation states that spacetime curvature is directly sourced by the energy and momentum content of whatever fields and matter are present. Mass, as in rest mass density, is only one component of t mu nu. Light, or more precisely the electromagnetic field, has its own energy density, momentum density, and pressure, so it contributes to t mu nu as well. That means, in principle, light does not just move in curved spacetime, it also helps curve spacetime. A beam of light has its own gravitational field, however small. In ordinary situations like room lights, lasers in a lab, or sunlight at Earth's distance, the gravitational effect of the light itself is minuscule, completely overwhelmed by the gravity of the massive objects nearby. It is still real in principle though, and in extreme environments, the contribution of radiation to gravity becomes important. In the early universe, when temperatures were extremely high and matter was ionized and coupled tightly to radiation, The total energy density was dominated by radiation, not by non-relativistic matter. The expansion rate of the universe in that era followed the rules for a radiation-dominated universe as encoded in the Friedmann equations, derived from general relativity. This is a concrete example where light and other relativistic particles contributed substantially to the overall curvature of spacetime and therefore to how light and matter moved. So, the summary for this segment is straightforward. Light feels gravity not because it has mass, but because in general relativity, motion is determined by spacetime geometry. All free systems, including light, follow geodesics. Light's geodesics are null and their shapes are fully determined. Once the metric is known, gravity affects light by bending these null paths and by altering the timing structure they pass through. In turn, light, by carrying energy and momentum, contributes to the energy-momentum tensor, and therefore in principle to the curvature. The interaction is two-way, but asymmetric in magnitude in most settings. This picture removes the need for any hidden photon mass, and replaces the old force on mass idea with a consistent rule where geometry governs motion for both massive objects and massless light. When a very massive cluster of galaxies sits between us and some much more distant galaxy, the cluster's gravity curves space-time strongly, and light from the background object has to travel through that curved region. The result is that the cluster acts as a gravitational lens. It can magnify the background galaxy, distort its apparent shape, and even split its image into several separate arcs or blobs or on the sky. This is not a guess. Deep images from Hubble, and more recently from JWST, show long thin arcs wrapped partway around clusters, smeared smudges that are stretched versions of normal galaxies, and clear cases where the same distant galaxy appears in multiple places, with the same spectrum and redshift. These observations are high-resolution, high-signal evidence that space-time around the cluster is not flat, and that light paths are being reshaped by that curvature. In particularly symmetric or well-aligned configurations, the effect of gravitational lensing becomes even cleaner to interpret. If a background galaxy or quasar sits almost exactly behind a foreground galaxy or cluster as seen from Earth, the light can be deflected into a ring-like structure around the lens. This is called an Einstein ring. The ring is not a separate object, it is the background source, whose light has been redirected by the curved space-time around the foreground mass. In other situations, a single background quasar can appear as 4 distinct points of light arranged around a foreground galaxy. This is a classic quad lens. In both cases, detailed modelling of how much the light is bent as a function of angle and position lets astronomers reconstruct the mass distribution in the lens. They can infer where the mass is concentrated, how it is spread out, and how much of it must be in the form of dark matter, which emits no light but still contributes to the curvature. The power of lensing goes beyond dramatic individual systems. It gives us a way to weigh galaxies and clusters without relying on how bright they are or how fast their stars are moving. The basic fact that the bending angle depends only on the total mass energy causing the curvature, not on its composition, means that if you can measure the deflection, you can infer the projected mass. Strong lensing, where we see obvious arcs and multiple images, gives very precise mass maps. In the central regions of clusters, weak lensing uses a statistical approach. Light from many distant galaxies is sheared slightly by large-scale structures. Each individual distortion is small, but by averaging over millions of background galaxies in wide-field surveys, we can recover the pattern of shear across the sky. From that pattern, cosmologists reconstruct the distribution of matter, particularly dark matter, on large scales, building maps of the cosmic web that do not depend on how the matter glows, only on how it bends light. Gravitational lensing also affects the travel time of light in systems where a background quasar is multiply imaged. Each image corresponds to light that has followed a different path through the curved space-time around the lens, those paths differ both in geometric length and in the depth of gravitational potential they traverse. Because of this, variability in the quasar's brightness shows up at slightly different times. In each image, one brightening might appear first in one image, and then days, weeks, or months later in another. By measuring these time delays accurately and combining them with a good lens mass model, astronomers can infer distances and test cosmological parameters, including the expansion rate of the universe. This works because the speed of light is fixed, so any difference in arrival times directly reflects differences in path and potential imposed by the spacetime geometry. Once again, light's journey becomes a direct probe of curvature, not of any supposed mass of the photon itself. Taken together, strong lensing with its striking arcs and rings, and weak lensing with its subtle statistical shears, plus the time delay measurements in quasar lenses, form a consistent set of tools. They show that light rays from very distant sources are being bent, stretched, and delayed in exactly the ways predicted by a general relativity. When mass and energy are present, these methods have become standard in modern astrophysics. They are used routinely to measure cluster masses, map dark matter, and test cosmological models, and at every step, the underlying principle stays the same. Spacetime is curved by energy and momentum. Light follows null geodesics in that curved spacetime, and what we observe on the sky is the visible record of those paths. You do not need to assign any rest mass to light. To explain lensing, you only need to accept that geometry, not a simple Newtonian formulae, governs how light travels. Near a black hole, spacetime is curved so strongly that the structure of possible paths for light changes qualitatively. There is a critical boundary called the event horizon. Outside this radius, some light can still escape to infinity given the right direction. Inside this radius, all future directed paths, including all null geodesics for light, lead inward toward the singular region. This is not a case of gravity pulling harder on photons as if it were a force getting stronger with distance. It is a geometric fact about which directions in space-time are available. Once you cross the event horizon, every possible direction that points into the future also points deeper into the whole. So any light emitted there, no matter how it is aimed locally, remains trapped. An observer far away can never receive those photons. Just outside the event horizon, the behaviour of light is already very different. Compared to weaker gravitational fields, there exists a special radius called the photon sphere, where light can, in principle, follow circular orbits around the black hole. This happens because the curvature is such that null geodesics can close on themselves in angle. For a non-spinning Schwarzschild black hole, this photon sphere lies at 1.5 times the Schwarzschild radius. These orbits are unstable. A small inward or outward perturbation sends the photon either plunging in or escaping outward, but the sphere still has observational consequences. Light from the background or from the accretion flow that passes close to this region can loop around the black hole one or more times before heading outward. This multiple orbiting increases the probability that some directions on the sky receive strongly lensed light and contributes to the bright ring-like structure predicted around black holes. The Event Horizon Telescope, a global array of radio telescopes, has directly imaged the immediate surroundings of two supermassive black holes, the one in the galaxy M87 and the one at the Milky Way's centre, Sigma A. The images, after careful processing, show a dark central region surrounded by a bright asymmetric ring or crescent. The dark area is not a photograph of the event horizon itself, but rather the shadow. It is the region on the sky where light rays traced backwards from the observer end up crossing the event horizon. Instead of reaching bright emitting material, the surrounding ring is formed by photons that skim close to the photon sphere and are bent, sometimes looping around the black hole before escaping. The brightness asymmetry is explained by relativistic beaming and Doppler effects. Gas moving toward us appears brighter. The key point is that the size and shape of this shadow and ring match detailed simulations based on general relativity. Given independent estimates of the black hole mass and spin, these observations provide a strong test of how light propagates in extremely curved space-time. Beyond the radio images, high-energy X-ray observations give us more information about light emitted very close to black holes. Gas in an accretion disk falls inward, heats up to tens of millions of degrees, and radiates strongly in X-rays. Embedded in this spectrum are emission lines from heavy elements, especially iron. In a flat space-time or weak gravity environment, these lines would be relatively narrow, centered at well-defined energies near a black hole. The combination of fast orbital motion and strong gravitational field alters them. Special relativistic Doppler shifts from gas moving toward or away from us broaden the line and skew it. General relativistic gravitational redshift shifts photons emitted deeper in the potential to lower energies by the time they reach us. The result is a broad asymmetric iron line profile, extending to lower energies. By fitting these distorted line shapes with models based on general relativity, astronomers can infer the inner radius of the accretion disk and the spin of the black hole. A faster spinning black hole allows the disk to extend closer to the horizon, increasing the relativistic distortions. Again, the data align well with the predictions of light moving along null geodesics in a curved spacetime described by Einstein's equations. All of these phenomena, event horizons blocking all future paths, photon spheres allowing unstable light orbits, bright rings formed by multiply lensed photons, and skewed X-ray lines produced near the inner disk, are different faces of the same underlying rule. Space-time near a black hole is extremely curved, and light, even without mass, must follow the null geodesics determined by that curvature. The failure of light to escape inside the horizon is not a breakdown of its speed. It still moves locally at c. It is a consequence of the fact that the structure of space-time leaves no escaping routes. What we observe from far away is the light that managed to travel along the last outward paths just outside the horizon, carrying with it detailed information about how gravity behaves in its strongest accessible regime. In general relativity, gravity does not just bend space, it also changes the rate at which time passes. This is a central part of the theory, and it has been measured in many ways. When you move closer to a massive body deeper into its gravitational potential, well, proper time, the time measured by a clock sitting there, runs more slowly. Compared with a clock far away, in weaker gravity, this is not a metaphor. It is a quantitative prediction, and it shows up directly in atomic clock experiments. If you place one very accurate atomic clock at sea level and another identical clock on a high mountain and compare them, you find that the higher clock ticks slightly faster. The difference is tiny but measurable. Modern clocks are so precise that even moving one by a few tens of centimeters in height changes the tick rate in a detectable way. This means that when light travels between regions of different gravitational potential, it is passing through layers of spacetime, where time is stretched or compressed relative to each other. Its frequency, which is cycles per unit time, and its wavelength, which is tied to frequency via the constant speed c, are therefore shifted by gravity. This is gravitational time dilation, directly encoded in the behavior of light. The effect on light's frequency when it climbs out of a gravitational well is called gravitational redshift. Consider photons emitted from the surface of a very compact star, such as a white dwarf. Near the surface, the gravitational potential is much deeper than it is far away. The photon starts with some frequency, set by the atomic process that emitted it. As the photon moves outward, it must climb to regions where time runs faster. From the perspective of an observer at infinity, the photon loses energy, not by slowing down, since the local speed of light remains key, but by having its frequency reduced. Since E equals h nu, lower energy means lower frequency. Lower frequency means longer wavelength, so the light is shifted toward the red part of the spectrum. Astronomers see this by looking at the spectral lines from known atomic transitions in the atmospheres of white dwarfs and other dense stars. Those lines appear at slightly longer wavelengths than they would if gravity were not present. The size of the shift matches the gravitational redshift predicted by general relativity based on the star's mass and radius. This is a clean, independent confirmation that time dilation in strong gravity directly affects light, changing its observed colour. The same mechanism operates near neutron stars and black holes. Even more strongly, photons emitted very close to a neutron star's surface or near the inner parts of a black hole accretion disk are highly redshifted when we detect them far away. In X-ray spectra, we see emission lines that are both broadened and shifted. The broadening comes from Doppler effects, due to fast orbital motion, while the net displacement of the line to lower energies is partly due to gravitational redshift. Together, these distortions encode how much spacetime is warped. Near the compact object, all of this is still the same basic story. Clocks deeper in the potential well tick more slowly. Light emitted there is stretched in frequency when compared with light from regions where time runs faster. Pulsars, which are rapidly rotating neutron stars, provide a very precise astrophysical testbed for these ideas. A pulsar emits narrow beams of radio waves locked to its rotation. As the star spins, those beams sweep past Earth, and we detect regular pulses. The timing of these pulses can be measured with incredible precision, sometimes to better than a microsecond over many years, in binary systems, where a pulsar orbits another neutron star or a white dwarf. Gravity affects both the orbital motion and the travel time of the radio pulses. As the pulsar moves in its orbit, the path length to Earth changes, giving a classical Doppler effect. But on top of that, there are relativistic time dilation and gravitational redshift effects. When the pulsar is deeper in the gravitational field, closer to its companion, its clock runs slightly slower compared to when it is farther away. This shows up as tiny variations in the pulse arrival times. Long-term monitoring of binary pulsars reveals a combination of effects, including orbital decay due to gravitational wave emission. Shapiro delays when pulses pass near the companion's gravitational potential and gravitational redshift. Associated with changing depth in the potential well, all of these align with the predictions of curved spacetime, and they are extracted from nothing but the timing of light, that is, radio waves, arriving at our telescopes. One famous example, the Hulse-Taylor binary pulsar, provided the first indirect evidence for gravitational waves by showing that the orbital period was shrinking at a rate precisely equal to what general relativity predicts for energy being carried away by gravitational radiation. But even apart from that, the detailed timing analysis required including gravitational time dilation and Shapiro delay to match the data. More recently, so-called double pulsar systems, where both stars are pulsars, have allowed even more stringent tests. You can think of these systems as natural laboratories where light in the form of radio pulses is constantly being sent through a strongly curved space-time geometry, and our measurements of its arrival times become a direct probe of how time itself is warped by gravity. If you pull these threads together, the picture is now fairly clear. Gravity, in Einstein's theory, alters the metric of space-time, both the spatial part and the temporal part, closer to a massive object. The time component of the metric is such that proper time intervals between events on a clock-world line are smaller compared to coordinate time than they are far away. This means a local clock, in stronger gravity, accumulates less time between two coordinate time slices than a clock in weaker gravity. Light, which connects events in space-time with null intervals, is not exempt from this structure. Its frequency, phase and travel time are all influenced by the way time is scaled. In different regions, light does not need rest mass. To undergo these changes, it only needs to exist in a space-time where the flow of time depends on position. So when you see light's frequency shift as it climbs out of a well, or signal timings change as pulses pass near a massive companion, you are really seeing time itself run at different rates in different places. Light, with its fixed local speed c, is forced to adapt by changing wavelength and by taking paths, whose effective travel time includes both spatial distance and the varying rate of time along the route. The bending and delay we observe are side effects of this deeper fact that gravity reshapes time, not just space. The answer to why light is affected by gravity therefore does not require any mass glued to the photon. It follows directly from the idea that space-time is curved, and that time dilation is part of that curvature. Once that is true, any signal that depends on cycles per unit time, and any path that depends on integrating over time, will show gravity's influence. Light fits both of those descriptions exactly. In Einstein's framework, the thing that creates space-time curvature is not mass alone, but the full energy momentum content. Encoded in the energy momentum tensor, this tensor includes energy density, momentum density, pressure and stress. Mass, in the sense of rest mass, is just one way that energy can be stored. Photons, even though they have no rest mass, carry energy and momentum, and they also create pressure when confined or streaming in a preferred direction, so they contribute to this tensor, and therefore, in principle, they curve space-time. This means that an intense beam of light, or a region filled with radiation, does technically generate its own gravitational field. The effect for light intensities we can produce in normal circumstances is extremely small, completely negligible compared with the gravity from ordinary matter around it. But conceptually, the rule is clear. Wherever there is energy, including light, there is a source for gravity. If you write Einstein's field equation schematically as g mu nu equals open parenthesis 8 pi g divided by c to the 4th power close parenthesis d mu nu, the left-hand side, g mu nu, describes how space-time is curved. The right-hand side, t mu nu, describes how energy and momentum are distributed for a gas of photons or for electromagnetic radiation. T mu nu is not zero. In fact, for pure radiation, the energy density is related to the pressure by a fixed relation. P equals rho c squared over 3. So you have a specific well-defined form of the energy momentum tensor. This can be plugged into the equations, and you can solve for what kind of space-time geometry is generated. So mathematically, there is no ambiguity. Radiation gravitates, whether you want to think of it as a source of gravity or not. The equations force that conclusion. To get an intuitive sense, imagine you have a very intense laser beam traveling through otherwise empty space. The beam carries energy per unit volume. It has a momentum flux along its direction, and it exerts a pressure if it hits a surface. All of those show up in tan. The effect on space-time curvature is proportional to the energy density of the beam times g over c to the power of 4, numerically g over c to the power of 4 is a very small factor. So unless the energy density is enormous, the curvature is tiny. For realistic laboratory lasers, the gravitational effect is so minuscule that there is no practical way with current technology to detect it against noise. Nonetheless, if you ask what general relativity predicts, the answer is yes. The beam slightly changes the geometry. Light does not just travel through the gravitational landscape, it adds a tiny contribution to that landscape as it moves. The place where radiation as a source of gravity really matters is not in small experiments, but in the global history of the universe. Right after the Big Bang, in the first tens of thousands of years, the universe was hot, dense, and filled with radiation and relativistic particles. At those high temperatures, matter was mostly in the form of particles moving at speeds close to c. The energy density in radiation, photons and neutrinos dominated over the energy in non-relativistic matter, like protons and neutrons that move more slowly. In this regime, the expansion rate of the universe is controlled mainly by the radiation energy density. The Friedmann equations, which apply general relativity to a homogeneous isotropic universe, show that in a radiation-dominated phase, the scale factor A of t, which measures the size of the universe, grows with time as t to the power 1/2, not as t squared over 3 as in a matter-dominated era. This difference is not just academic, it leaves signatures in how the early universe evolves. We see evidence for this radiation-dominated era in the cosmic microwave background. The CMB is the relic radiation, left over from about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms, letting photons travel freely. The uniformity and spectrum of this radiation tell us that earlier the universe was in thermal equilibrium at very high temperatures. Its small anisotropies, the tiny temperature fluctuations we map today, reflect acoustic oscillations in the hot plasma. Driven by the interplay of radiation pressure and gravity, the pattern of these fluctuations depends sensitively on the relative contributions of radiation and matter to the total energy density at different times. Observations of the CMB agree with a cosmological model where early times radiation, including light, was the dominant gravitational source. Later, as the universe expanded and cooled, matter took over, but in that first phase, light created gravity, in the sense that its energy density was the main term driving curvature and expansion. Thinking on smaller, more contained scales, consider a simple system, a perfectly reflecting box in otherwise empty space. If the box is empty, it has some rest mass, set by the atoms in its walls. Now, imagine you pump electromagnetic radiation into the box, bouncing around inside since the walls are perfectly reflecting. The radiation is trapped. Its energy cannot leave. The total energy of the system therefore increases. Relativity tells you that the effective gravitational mass of the box, measured by how strongly it would attract a distant object, also increases, even though you have not added any new rest mass in the usual sense. You have added energy in the form of light, and that energy contributes to the gravitational field. If you could weigh the box with the light inside versus with no light, in principle the full box would register a slightly larger weight. The difference is extremely small, unless the radiation energy is enormous, but the principle is clear. Trapped light adds to gravitational mass. Stars? Give another, more realistic example. In a star, nuclear fusion in the core converts rest mass into radiation. The photons produced do not immediately escape, they scatter countless times and can be trapped for long periods, especially in dense regions. The radiation energy density in the interior can be very high, and radiation pressure contributes significantly to the balance between outward pressure and inward gravity. In massive stars, radiation pressure is a key term in the stellar structure equations, the total gravitational mass of the star. What you would infer from the orbits of planets or binary companions includes the contributions from both rest mass of particles and the energy stored in radiation. Stellar models that successfully match observed luminosities, radii and lifetimes, require that radiation's energy be included as part of the gravitational source. Again, photons inside the star contribute to the gravity that holds the star together. You can push this idea further in theoretical work. Physicists have explored solutions to Einstein's equations where radiation is such a dominant component that it, together with its own pressure, supports a configuration that resembles a star, but is largely composed of radiation. These are sometimes called radiation stars, or in related contexts, photon stars. In some models, electromagnetic radiation is trapped in a gravitational well, and its pressure balances its self-gravity, forming a kind of equilibrium. However, such objects tend to be unstable. Small perturbations can make them collapse further or disperse, so they are not expected to be common or long-lived. In the real universe, nonetheless, the exercise shows logically that light, if sufficiently concentrated, can both generate gravity and be supported by the pressure arising from that same radiation. Within general relativity's equations, light is not merely a test field, probing a background. It can be part of the active source that shapes that background. There are also solutions where gravitational fields are sourced by other massless fields. For example, in some models, bundles of gravitational waves or electromagnetic waves known as geons in older literature are held together by their own self-gravity. Again, these are mostly theoretical constructs, and their stability is limited. But they underscore the same point. What matters for gravity is energy and momentum, not rest mass alone. If you pack enough energy, even in a massless field, into a small enough region, its gravitational effects cannot be ignored. Bringing this back to the main question, does light create gravity too? The consistent answer from general relativity is yes. In principle, light contributes to space-time curvature through its energy, momentum, and pressure. In many everyday and laboratory contexts, the effect is far too small to notice compared to the gravity from matter. So we safely treat light as a test field, reacting to gravity, but not creating it. In the early universe, in star interiors, and in extreme theoretical constructs, the gravitational role of radiation becomes important, sometimes even dominant. This confirms a key idea. In Einstein's universe, light is not just a passive traveller, moving through a fixed gravitational stage. It is also, when dense enough, part of the cast that determines the shape of that stage. In classical physics, you are often given two separate pictures of light. One says light is a wave, spreading out, interfering, diffracting. Another says light is made of particles, photons, arriving as discrete packets in detectors. Quantum field theory takes both of these and replaces them with a more precise statement. There is an electromagnetic field that exists everywhere in space, and a photon is a discrete excitation or quantum of that field. There is no tiny solid marble flying along a definite track. Instead, the field has modes like standing waves in a cavity, and those modes can be occupied by zero, one or many quanta. A single photon is the one quantum state. For a given mode, multiple photons are higher occupation numbers, and classical light waves correspond to large numbers of photons arranged in coherent states. This view removes the ambiguity. You're not switching between wave and particle models. You're talking about one underlying field, which has both wave-like propagation and particle-like quanta. In this language, processes like the photoelectric effect, Compton scattering or emission and absorption in atoms are described by intersections between the electromagnetic field and matter fields, quantized as well. When an atom emits a photon, its internal state transitions and the electromagnetic field goes from one excitation pattern to another, with one more quantum in a particular mode. When a detector clicks, it is not because a little billiard ball hit it, it is because the field interacted with charges in the detector, transferring a discrete amount of energy and momentum equal to one quantum. This is why you see counting statistics such as Poisson distributions in low-light experiments. The field is continuous in space, but its energy exchange with matter is quantized in units of nu, where h is Planck's constant and nu is the frequency. Quantum fields do not live in an abstract separate arena. They live on space-time. The equations that govern the electromagnetic field, like Maxwell's equations, can be written on flat space-time, or on curved spacetime in flat Minkowski spacetime, you get the usual propagation at speed c, plane wave solutions and so on. In a curved spacetime, the derivatives in the equations are replaced by covariant derivatives that include the metric. The light cones, which define the allowed directions for light propagation, depend on that metric. When you quantize the field, you do so on this curved background. The field operators propagate according to the geometry. They do not ask what is the gravitational force on a photon. Instead, their allowed solutions are constrained by the space-time metric. In that sense, gravity affects light by modifying the structure of the field equations through the geometry. This fields on a background view is how most practical calculations are done. In astrophysics and cosmology, you treat the geometry, MG, as given by general relativity at least. Approximately then you consider quantum fields on top, photons in an expanding universe, have their wavelengths stretched. Because the Sale factor in the metric changes with time, gravitational redshift is understood as the effect of moving between regions with different metric components. For the time coordinate, lensing is described by solving for null geodesics, which are also the characteristics along which field modes propagate. The key point is that you do not bolt gravity on as an extra force term in the photon Hamiltonian, you build it in through the geometry that the field lives on. Hawking radiation is one of the most famous predictions that arises when you combine quantum fields with curved spacetime. Consider a black hole. In classical general relativity, the event horizon is a one-way surface. Nothing escapes. But when you take a quantum field and ask, what does the vacuum look like near the horizon? In a curved spacetime, you find that an observer at infinity will see a thermal flux of particles emitted by the black hole. This Hawking radiation gives the black hole an effective temperature inversely proportional to its mass. For astrophysical black holes, the temperature is extremely low and the radiation is swamped by other sources, so we have not directly detected it. But the derivation is a concrete example of quantum field theory in curved spacetime, predicting new phenomena that would not appear in flat space. Because direct detection from real black holes is hard, researchers have built analog systems in the lab where something behaves like an effective horizon. Fluids flowing faster than the speed of sound in a certain region can create a sonic horizon. For phonons, light propagating in specially engineered optical media can experience an effective horizon as well. In these systems, the equations governing the perturbations look mathematically similar to quantum fields near a black hole horizon. Experiments have observed Hawking-like emission of phonons or photons in these analogues. The spectra and correlations match the theoretical expectations. These do not prove that astrophysical Hawking radiation exists, but they strongly support the underlying framework. Quantum fields, plus an effective curved geometry, produce particle creation effects that align with the theory. More generally, quantum field theory on curved spacetime also predicts effects like particle creation in an expanding universe, or in non-inertial frames. The Unruh effect says that an accelerating observer in flat space will see a thermal bath of particles. Even though an inertial observer sees vacuum, the details depend on how the field modes are defined, relative to the geometry and the observer's world line. Again, these are not about forces acting on photons, they are about how the field's notion of vacuum and particle depends on the space-time backdrop, and how observers embedded in that backdrop describe the field. At a deeper level, we do not yet have a full experimentally established quantum theory of gravity. We have general relativity, which treats space-time as a classical smooth geometric object, and we have quantum field theory which quantizes matter and gauge fields. Like the electromagnetic field, the combination we actually use in most calculations is a hybrid. We quantize fields on a classical spacetime background. We let that background be curved according to Einstein's equations, sourced by the expectation value of the energy-momentum tensor. In some approximations, this is called semiclassical gravity. It works exceptionally well for all the regimes we have tested: light bending, gravitational redshift, lensing, cosmological redshift, pulsar timing, black hole shadows, can all be modelled by quantum electromagnetic fields moving in a spacetime whose curvature is determined by classical general relativity. What we are missing is a theory where spacetime itself is quantized in a way compatible with the quantum nature of matter fields. Candidates like string theory, loop quantum gravity, and others aim to provide this, but none is confirmed by direct experimental evidence yet. However, for the question you're asking why gravity affects light, we do not need the full quantum gravity answer. The semi-classical picture is enough. Photons are quanta of the electromagnetic field. That field lives on space-time. Space-time is curved by energy and momentum, including that of light itself, and the propagation of the field is governed by the geometry. The fact that every observation so far fits this hybrid description is why we are confident in using it as the working explanation. So, the clean summary for this segment is: a photon is not a tiny mass-bearing particle. It is a quantum of a field that fills space-time. Gravity, in turn, is not a force acting within a fixed stage. It is the curvature of that space-time. When space-time is curved, the electromagnetic field's equations are modified via the metric. The null paths along which disturbances propagate are bent. Their frequencies are shifted. Their travel times are altered. Light is affected by gravity because the field it comes from is constrained by the warped geometry. You live conceptually in a universe where quantum fields ride on a curved classical spacetime, and that picture already explains why massless photons respond so precisely to gravity. In classical physics, light was first modelled as a wave in an electromagnetic field. You have electric and magnetic fields oscillating in space and time, obeying Maxwell's equations. Later experiments like the photoelectric effect and Compton scattering showed that light also behaves as if its energy comes in discrete chunks, photons. Early on, this was described with the language of wave-particle duality, but that phrasing is limited. In modern quantum field theory, the more precise picture is there is a quantum electromagnetic field defined everywhere in space-time, and what we call a photon is a discrete excitation or quantum of that field. There is no tiny solid marble flying through space with a fixed trajectory. Instead, the field is the fundamental object, and the photon is a localized packet of field vibration. With quantized energy and momentum, this framework consistently reproduces both the wave-like interference of light and the particle-like detection events in detectors without switching models back and forth. Quantum field theory treats all particles, not just photons. In this way, electrons, quarks, neutrinos are excitations of their respective fields. The electromagnetic field is special in that it is massless, so its excitations, photons, always propagate at the speed of light in vacuum. The properties of a single photon, such as its energy, E equals he nu, and momentum, P equals E over c, come from the way the field is quantized and from the symmetries of space-time. Importantly, even in vacuum, the field has allowed modes at different frequencies and directions. Quantization tells you that the field can occupy states with different numbers of quanta in each mode. Gravity, in this language, does not directly pull on photons as particles. Instead, the electromagnetic field obeys equations that are modified by the presence of curved spacetime, and the quantized excitations follow from those field equations. Quantum fields are not defined in an abstract detached space. They are defined on spacetime itself. In flat spacetime, you use the Minkowski metric and Lorentz symmetry to define what energy, momentum, and particles mean. In curved spacetime, the background geometry is different. The metric is no longer flat, and global symmetries may be absent. The electromagnetic field still satisfies a generalization of Maxwell's equations written in a covariant form using the curved metric. This means the allowed solutions for the field, the mode structure, and how disturbances propagate are all controlled by the geometry. When you quantize the field on this curved background, the notion of a photon becomes tied to that geometry. Light does not need to ask what force is acting on me. Its behavior is fixed by how the underlying field responds to the spacetime metric. Photons then follow the null geodesics associated with that metric as a consequence of how their wave functions evolve. One of the striking theoretical results of combining quantum field theory with curved spacetime is Hawking radiation. If you take a quantum field in the background of a black hole spacetime and analyze how modes behave near the event horizon, you find that the horizon causes a mixing of what different observers call positive and negative frequency modes. To an observer far away, the vacuum near the horizon is not empty, but appears to emit a thermal spectrum of particles. In the case of the electromagnetic field that would include photons, this is Hawking radiation. In principle, real black holes radiate and slowly lose mass. In practice, for stellar mass or larger black holes, the temperature is so low that the radiation is far too weak to detect against other astrophysical backgrounds, so we do not yet have a direct observation. However, analogous systems in the lab have given supportive evidence. Researchers have built analog horizons in fluids, optical fibers, and other media, where waves are trapped in a way mathematically similar to a horizon for light, for example. In a flowing fluid, if the flow speed exceeds the wave speed in some region, that region can act as an effective horizon for surface waves. When quantum or classical fields propagate in these effective curved geometries, one can look for spontaneous emission of quanta analogous to Hawking radiation. Experiments have reported signals consistent with such Hawking-like emission for phonons in fluids or for light in nonlinear optical media. These are not black holes, but they show that when you combine a field with a horizon-like geometry, particle creation effects appear, matching the predictions from quantum field theory on curved backgrounds. Even with these advances, we do not yet have a complete fundamental theory that unifies quantum mechanics and gravity. General relativity treats spacetime curvature classically as a smooth geometric object. Quantum field theory treats fields quantum and mechanically on a fixed background. The framework where we place quantum fields on a classical curved spacetime is an approximation, but it has been extremely successful. All the phenomena discussed earlier, light bending, gravitational redshift, Shapiro delay, gravitational lensing, pulsar timing, can be described by taking classical general relativity to provide the metric, and then letting the electromagnetic field propagate, classically or quantum mechanically, on that metric. In this hybrid picture, gravitons, the hypothetical quanta of the gravitational field, and full quantum fluctuations of spacetime itself are ignored because in the regimes we have probed experimentally, those effects are expected to be extremely small. So when you ask why gravity affects light, in the modern language the answer is because the electromagnetic field lives on and responds to spacetime geometry photons are. Quantized excitations of that field, their trajectories and frequencies are determined by how their wave functions evolve on the curved background given by general relativity. A full quantum gravity theory would refine this picture at very high energies or extreme curvatures, but for all current tests, quantum fields on a classical curved spacetime are sufficient. This is the practical working framework that successfully links massless photons, curved spacetime, and all the observed phenomena to show gravity's influence on light. In special relativity, there is a hard rule. There is a maximum speed for any influence, any signal, any cause and effect. That maximum is encoded in the structure of spacetime itself, in flat spacetime. That limit takes the numerical value we call the speed of light in vacuum. C. Light is not special because it chooses that speed. Instead, anything that has zero rest mass must move at this speed, and anything that has non-zero rest mass can never be accelerated all the way up to it. The relativistic energy relation, E squared equals P squared C squared plus M squared C to the fourth power, tells you this directly for m's greater than 0. As you push the speed closer to C, the energy required grows without bound, so you cannot reach C with finite energy for m equals 0. The only consistent solution is to move at exactly C. Photons, as massless excitations of the electromagnetic field, are therefore locked to this speed. In vacuum locally, there is no freedom to speed up or slow down. They always propagate at C. When you bring gravity into the picture, you move from special relativity's flat spacetime to general relativity's curved spacetime. The key point is that the speed of light is C statement remains true locally. If you zoom in on a small enough region of spacetime, you can always choose coordinates in which the laws of physics look. To a good approximation, like special relativity, in that small patch, light still travels at key and no signal exceeds that speed. What changes? In curved spacetime are the relationships between different regions. Globally, distances and time intervals between events are distorted by curvature, so light can take longer to get from point A to point B than a naive straight line flat geometry calculation would suggest. Its path can bend, its frequency can be shifted, but these are changes in the geometry and in the coordinate description, not violations of the local speed limit. Along its path in its local frame, light always moves at C. This distinction between local behavior and global geometry is crucial. When you say that light is delayed as it passes near a massive object or that its path is curved, you are describing the integrated effect of moving through a space-time with a non-trivial metric. The Shapiro delay, for example, is a longer travel time due to both path bending and gravitational time dilation. Similarly, gravitational redshift is a change in frequency tied to different clock rates at emission and detection points. None of these require light to move slower than c. At any small segment of its journey, they arise because when you integrate along a null geodesic in a curved metric, the coordinate time difference between emission and reception is different from what it would be in a flat metric, so you get apparent delays and shifts while the local speed stays fixed. Observationally, we can test how robust this constancy of light speed is by looking at high-energy phenomena over huge distances. Gamma ray bursts are powerful explosions in distant galaxies that emit photons over a wide range of energies from X-rays up to very high-energy gamma rays. If the speed of light in vacuum depended even slightly on photon energy, then as these photons travel billions of light years, the tiny difference in speeds would accumulate into noticeable differences in arrival times. High-energy photons might arrive seconds or minutes earlier or later than lower-energy ones, beyond any delays generated at the source. Astronomers have carefully examined the light curves of many gamma-ray bursts, comparing the arrival times of different energy bands after accounting for source physics. They find no significant energy-dependent lag. Consistent with a single propagation speed, the constraints from these observations place very tight limits on any hypothetical deviations from a constant in vacuum, stronger than what we can achieve in the lab. Similar tests are done with flares from active galactic nuclei and with fast radio bursts, in these cases too, after you correct for dispersion caused by ordinary matter. Like electrons in intergalactic space, the residual signal is consistent with energy-independent propagation at thick over cosmological distances. This backs up experimentally the idea that light speed in vacuum is fixed and does not vary with frequency or energy. in any way large enough to explain gravitational effects, the bending, delays and redshifts we see must therefore be explained by spacetime curvature and time dilation, not by letting photons slow down under gravity. Putting this together, you get a clear mental upgrade. Light speed, in the local sense, is non-negotiable. It is fixed to c for massless quanta. What is flexible is the geometry that light moves through. Gravity in general relativity changes the metric, which in turn changes what we mean by straight paths, distances, and time intervals. Null geodesics, the straightest paths available to light, twist and curve in the presence of mass and energy. Coordinated distances stretch or compress. Coordinate times between events include gravitational time dilation. The result is that from a distant observer's viewpoint, light can appear to bend, arrive late, or be shifted in frequency. None of that requires altering its local speed, it only requires accepting that the underlying spacetime is not flat. So the final picture is speed fixed. Paths and clocks shaped by gravity. Light is affected by gravity because gravity changes the geometry, not because it changes the intrinsic speed of the photon. A very common misunderstanding that sits quietly in the background of people's thinking is the idea that gravity pulls more. On heavier things, in everyday life, this seems true. You pick up a heavier object and it feels harder to lift. You stand on a weighing scale, and the reading scales with your mass. Mathematically, we say weight equals mass times. Gravitational acceleration, W equals mg, so doubling the mass doubles the weight. However, the key point is that in a given gravitational field, the acceleration g is the same for all freely falling objects. If you drop a hammer and a feather, in an ideal vacuum with no air resistance, they fall with the same acceleration and hit the ground together. This was shown dramatically during the Apollo 15 mission on the Moon. Where there is no air to slow the feather, the hammer and feather fell side by side and landed at the same time, in general relativity language. This happens because in freefall, all objects follow the same space-time geometry, the same geodesics, regardless of their mass or their composition. Heavier things feel a larger force, but they also have more inertia, and those two effects cancel in the acceleration. Light fits into this picture by following null geodesics. Its behaviour is fixed by the geometry, not by its mass. So there is no contradiction between massless light and falling with gravity once you focus on the shared geometry rather than on force intuition. Another common attempt to resolve the puzzle is to say, maybe photons actually have a tiny non-zero mass. Then gravity could pull on them in a Newtonian way, and that would explain bending. On the surface, this sounds reasonable, but it runs into serious problems with precise experiments and observations. If the photon had even a very small mass, the equations of electromagnetism would be modified. The range and behaviour of static electric and magnetic fields would change slightly. Instead of a perfect 1 over a squared force law, you would get an exponential suppression over very long distances. We can test this by looking at planetary and galactic magnetic fields and by measuring how electromagnetic forces behave in the lab. The absence of any detectable deviation lets physicists place extremely tight upper limits on any possible photon mass. Current bounds are so strict that any photon mass, if it exists at all, is far too small to produce the observed gravitational deflection of light. In other words, you cannot get the bending we see by assigning a tiny mass to photons without contradicting electromagnetism experiments. The curvature-based explanation from general relativity matches the data, without needing to violate those constraints. A related misconception is to treat gravity as a force field that directly pulls on photons, as if there were a gravitational force term in the photon equations of motion. In Newtonian gravity, you think of a gravitational force acting on a mass, and then you solve F equals ma. To get acceleration in general relativity, That is not the correct structure. There is no separate gravitational force in the fundamental equations. Instead, space-time is curved and free particles, including photons, follow geodesics in that curved space-time. The same mathematical machinery that gives planetary orbits as time-like geodesics gives light paths as null geodesics. You do not write down gravity pulls on photons. You write down the geodesic equation with the metric determined by Einstein's field equations. And then you see how null trajectories behave. The bending of light, the gravitational redshift, the Shapiro delay, all come out of that single framework. There is no extra coupling term that says, apply a special gravitational force to photons, which is why trying to think of gravity as a force that grabs light leads you away from how the theory is actually constructed. Once you adjust your mental model, light becomes not a problem for gravity, but one of the best tools for probing gravity, because photons interact weakly with matter. Compared with particles like protons or electrons, they can travel huge distances. Through interstellar and intergalactic space, mostly tracing only the effects of space-time curvature. When you see starlight deflected around the sun during an eclipse, when you observe giant arcs and Einstein rings around galaxy clusters, when you look at the bright ring and shadow near a black hole, when you detect small timing shifts in pulsar signals or brightness changes in lensed quasars, you are watching light act as a geometry detector. It is following the null geodesics carved out by the distribution of mass and energy and bringing you information about that curvature in a clean way across vast scales. The consistent story tying all of this together is not gravity pulls harder on heavy things and secretly on photons, but gravity is the geometry of space-time, and light, like everything else, follows that geometry. Once you adopt that view, the old misconceptions fall away, and the idea of massless light being affected by gravity stops looking like a paradox and starts looking like a straightforward consequence of the underlying rules. In binary pulsar systems, you have at least one neutron star emitting very regular radio pulses, orbiting a companion in a tight relativistic orbit. Because neutron stars are so compact and massive, their mutual gravity is strong, and their orbital speeds are a significant fraction of the speed of light. General relativity predicts that such a system will radiate. Gravitational waves carrying away orbital energy, which causes the orbit to shrink and the period to decrease over time, by timing the arrival of the radio pulses with microsecond precision over many years, astronomers can reconstruct the orbital motion and measure how the orbital period changes. The first famous example, the Hulse-Taylor pulsar, showed that the orbital period was decaying at a rate exactly in line with the energy loss predicted by general relativity. Beyond that, detailed analysis of pulse arrival times also had to include effects like gravitational redshift, time dilation, and Shapiro delay. As the pulses travel through the curved space-time near the companion, every one of those corrections match the relativistic calculations. Binary pulsars therefore act as stress tests for the theory. In strong field conditions, and the behavior of light from the pulsar is a key observable. Gravitational waves detected directly by instruments like LIGO and Virgo are another extreme test. These waves are ripples in space-time curvature produced by events like merging black holes and neutron stars. As a gravitational wave passes through a region, it periodically stretches and squeezes distances in specific directions. If a light beam is travelling through that region, its path length and the timing of its arrival are slightly modulated. Each LIGO interferometer is essentially a device that measures tiny changes in the time it takes for laser light to travel up and down its arms as a wave passes. General relativity predicts exactly how the space-time metric should oscillate, and the observed signals match those predictions when we also detect electromagnetic counterparts, for example light from a neutron star merger. We can compare the arrival times of gravitational waves and photons over cosmological distances. So far, they arrive within very small time differences. Once you correct for source physics, which strongly supports the idea that both follow the same spacetime geometry and that light still travels at sea even in the presence of dynamic curvature. On the larger scales, cosmology gives another set of tests. Light from distant supernovae, particularly type A supernovae, travels to us across billions of light years. In an expanding curved spacetime, the observed brightness and redshift of these supernovae, as a function of distance, do not follow the pattern expected from a universe that expands at a constant or slowing rate. Instead, they revealed that the expansion is accelerating. This discovery was made by fitting the supernova data with cosmological models that assume light follows null geodetics in a Friedmann-Lemaitre-Robertson-Walker spacetime with general relativity as the underlying theory of gravity. To match the observations, you need a component like dark energy or a cosmological constant, but you do not need to modify how light responds to curvature. More recent data from baryon acoustic oscillations, the cosmic microwave background, and gravitational lensing all use light as the messenger, and they fit into a single, self-consistent model where photons are massless, move at sea, and propagate according to general relativity. Across these different regimes, binary neutron stars with strong local curvature, gravitational waves dynamically altering space-time, and light crossing cosmological distances in an evolving universe, the same rules keep working. Light follows null geodesics in the metric given by Einstein's equations. Its speed is fixed locally. Its frequency and timing are influenced by curvature and expansion, not by any hidden mass or special force. Every time we push the theory to higher precision or more extreme environments, we look for discrepancies that might signal the need for a new framework. So far in all tests where light is involved, from pulsar timing to LIGO to high redshift supernovae, its behaviour is exactly what you would expect for a massless but energetic field living on a curved space-time. That does not mean general relativity is the final word. At very high energies or near singularities, we expect quantum gravity effects to matter, and we actively search for deviations, using more sensitive instruments and more distant or violent sources. But right now, the empirical status is simple. Wherever we can measure both gravity and light carefully, light behaves perfectly as if the geometry picture is correct. There is no sign that photons are violating the rules or that they require a fundamentally different treatment. As far as experiments go, light never misbehaves. When it comes to gravity, it is one of the cleanest, most reliable probes of how spacetime is structured. Modern technology quietly assumes that light is massless, and that spacetime is curved. One of the clearest examples is the Global Positioning System. GPS satellites orbit Earth, carrying very stable atomic clocks. They continually broadcast their time readings, encoded in radio signals. Those signals are light in the microwave part of the spectrum. Your receiver on the ground listens to several satellites at once and uses the travel time of those signals to triangulate your position. For this to work, the timing has to be extremely precise. Errors of a few tens of nanoseconds translate into position errors of meters. In Earth's gravitational field, clocks on satellites run at a different rate than clocks on the ground. General relativity says clocks higher up in weaker gravity tick faster. Special relativity says moving clocks tick slower. Relative to a stationary observer in orbit, both effects are present. Engineers pre-adjust the satellite clocks and continuously correct the data using the formulas from relativity. Without these corrections, GPS positions would drift by kilometers per day. The fact that the system works as well as it does is practical evidence that light travelling in a curved spacetime behaves exactly as general relativity says. Gravitational lensing, which we discussed as evidence, is also used as a tool to extend what our telescopes can see. When a massive galaxy cluster lies between us and a much more distant galaxy, The cluster's gravity magnifies and distorts the background light. This magnification can boost the brightness of very distant, very faint galaxies, making them observable. When they would otherwise be below detection limits, astronomers deliberately target known lensing clusters and point instruments like Hubble and JWST at them. The foreground cluster acts like a natural telescope upgrade for JWST. This has been crucial in the search for early galaxies whose light has been travelling for more than 13 billion years. That light has also been stretched by cosmic expansion into the infrared and bent and magnified by intervening structures. When we model these systems, we use the rules of null geodesics in curved spacetime to reconstruct the original properties of the source. The success of these reconstructions and the consistency across different wavelengths depends on treating light as massless and governed by the geometry, not by some ad hoc force. The cosmic microwave background, CMB, provides another layer of technology-like use, even though it is observational rather than engineering. The CMB is a nearly uniform bath of microwave photons, left over from the early universe. Small fluctuations in its temperature and polarization encode information about the initial conditions and about how structures grew over time. As these photons travel from the surface of a last scattering to us, they are not moving through a static empty space. They cross a universe filled with galaxies, clusters, and dark matter. Their paths are slightly deflected. By all this structure, this effect called CMB lensing introduces tiny distortions in the observed pattern. By measuring those distortions statistically, cosmologists can reconstruct the projected mass distribution across large areas of the sky. This lets them map dark matter and test models of structure formation. The analysis assumes that CMB photons are massless and follow null geodesics in the evolving spacetime metric. The excellent agreement between the inferred mass distribution and independent probes like galaxy surveys and weak lensing of galaxies supports that picture. Looking ahead, future technology will rely even more heavily on understanding how light behaves in gravitational fields. Proposals for interplanetary navigation systems involve laser links between spacecraft and ground stations, or between spacecraft themselves. Extremely precise timing and distance measurements over millions or billions of kilometers require full relativistic modeling of how signals propagate through the gravitational fields of the Sun, planets, and possibly massive moons. As we build more accurate atomic clocks and deploy them in space, relativistic time dilation and the curvature of space-time become design-level considerations, not small corrections. Missions that test fundamental physics, like measurements of the gravitational constant, searches for tiny deviations from general relativity, or attempts to detect low-frequency gravitational waves, all use light or other electromagnetic signals as the carrier of information, and all compute their expected signals using the same basic assumption. Light is massless, its local speed is fixed, and its path, phase, and arrival time are determined by the geometry it travels through. In that sense, the concept massless light in curved space-time is not just a theoretical idea, it is baked into instruments, networks, and navigation systems that we already use, and into the ones we plan to build. When you compress everything you've heard so far into one sentence, it goes like this. Light is affected by gravity, not because it secretly has mass, but because gravity, in Einstein's theory, is not a force pulling on mass, it is the curvature of space-time created by energy and momentum. Light has no rest mass. You can never ride alongside a photon and see it sitting still. But it absolutely carries energy and momentum. Those quantities appear in the energy momentum tensor, which sources curvature, so photons have to follow the curved geometry. Just like planets, just like freely falling rocks, they travel along null geodesics in whatever space-time exists, and that is why their paths bend, their frequencies shift, and their travel times change. In gravitational fields, The simple story many people grow up with says gravity is a force between masses. That picture works well for slow-moving objects in weak gravitational fields, like apples falling or planets orbiting gently far from anything extreme. But as soon as you bring in light, or you approach very strong fields like those near black holes, or you talk about the early universe, that story breaks down. If gravity were only a force between masses, then truly massless light would be invisible to it. Eddington's eclipse measurements, gravitational lensing by galaxy clusters, Shapiro delays, gravitational redshift, and the behavior of light near black holes all contradict that. Oh, the early universe, where radiation dominated the energy budget, contradicts it too. The updated story that fits all of those cases is that objects with mass and light without rest mass both respond to the same geometric rules. They follow the geodesics determined by the curvature. Their different properties only change which type of geodesic they can follow, time-like for massive objects, null for light, not whether they feel gravity at all. With that new framework in mind, you can now look at a wide range of phenomena and summarize them with one consistent chain of reasoning. When you see a dramatic gravitational lens image with arcs wrapped around a cluster, what's happening is the mass and energy in that cluster curve spacetime. The curvature defines a family of null geodesics. Background photons follow those geodesics and arrive at Earth from different apparent directions, creating multiple images, magnification and distortion. When you look at the shadow of a black hole, you are seeing where null geodesics, aimed from your telescope back into the scene, end up crossing the event horizon. The bright ring around the shadow is made of photons that skim the photon sphere and escape along bent paths. When your phone's GPS app gives you a position somewhere on Earth, it is using timing signals encoded in light, sent from satellites, whose clocks and signal paths are influenced by Earth's gravitational potential. Special and general relativistic corrections are applied to account for time dilation and curved space-time. If they weren't, your location would quickly become useless. The same three-step logic applies everywhere. Mass and energy curve. Space-time? Curved space-time tells matter and light how to move, and light, obeying the straightest possible paths in that curved structure, looks bent, delayed, or redshifted to us. The deeper shift, the real mind-bender in all of this, is not that light bends, the surprising part once you strip away the old Newtonian habits, is that space and time themselves are flexible. The distances between points and the intervals between events are not fixed by some rigid background stage. They depend on the distribution of energy and momentum. When that distribution changes, the geometry changes. Light, because it is massless, because it always travels at sea locally, is an especially clean tracer of that geometry. It doesn't get stuck in material. It mostly ignores messy microphysics. It just follows the null geodesics. If space-time is warped, its path and its frequency record that warp. So the bending of light is not a glitch or a loophole. It is one of the clearest, most direct signatures that space-time is curved at all. Once you get used to that, the phrase massless light affected by gravity stops being a paradox you need to explain away and becomes a precise, compact summary of how the universe actually works. Gravity is geometry, light is an obedient follower of geometry, and nearly everything we see in the sky is that simple rule written in photons. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.